Um, yeah. Hi, everyone. Welcome to GOCC. Today, we're so glad to have William Dugan from UMass Amherst speaking. Before we start, I just want to remind us about the community statement. In short, it's that we're all learning, everyone has something to contribute, and no one has all the answers. I'll monitor the chat for questions, but people can also unmute. We'll see how everything goes. Yeah. With that, take it away, William.
Okay, thank you so much. And maybe before I begin, I want to say, of course, a huge thank you to you guys. I think all the organizers, thank you for the invitation, but especially this is a huge service that you guys do. Like I was thinking of this today, it's really amazing that you put on this colloquium. It's a great opportunity for us, and just I learned a lot in the talk last week. So thank you, a huge thank you for keeping this up. Yeah, so side note, there is a surprising connection between my talk and Kimberly's talk from last week. It's kind of a side note, so if I forget to mention it by the end of the talk, then please remind me and I will mention something. Okay, so yeah, this is F vectors of flow polytopes for the complete graph. So this is a single author paper that I put out this past week. But this is part of my dissertation, so I should say so much of this has been influenced by my advisor, Alejandro Morales. So huge, of course, thank you to him, and single author work, but this isn't to say that he had a lot of influence. Oh, there we go. Okay, so brief overview before we begin. I'll start by telling you what is a flow polytope, because that's what this talk is about. And then I will tell you some technology we have for talking about faces of flow polytopes. We'll go into the main results and then wrap up with final remarks. The other disclaimer is that the first half of the talk will be, I think, quite nice. The second half of the talk becomes a little bit technical. And the reason for this is because there's nothing super deep, like combinatorially or mathematically, but there's some technical details involved in the proofs. And I wanted to make sure that people, watching, if they like what they saw, they could, continue, branch off in different directions. And so I wanted to make sure that they had to, anyone watching has tools to do that. So if there comes a point where you're like, oh, this is getting kind of technical, then we've reached that spot. All right, so to start with some motivation, we're motivated by this particular polytope, the Chan-Robbins-Yuen polytope, denoted cry-n. This is of order n, or indexed by number m. It's the convex hull of certain n by n permutation matrices. So these are permutation matrices that have support in this red region here. So the non-zero elements of the permutation matrix have satisfied J is bigger than or equal to I plus 2. And this polytope is famous for many different reasons. One of the reasons is that it has normalized volume equal to the product of the first n minus 2 Catalan numbers. So this was proven by Zauberger in 1998. But one of the reasons that Cry has produced so much interest in the research community is that Catalan numbers, we think of them as our numbers, these combinatorial numbers, and yet there's no combinatorial proof of this fact known to date. So this has been driving a lot of research in the community. It's also famous for other reasons as well. So it's also, you may have come across it in the context of the Birkhoff polytope. Cry is a face of the Birkhoff polytope of dimension n choose 2 and has 2 to the n minus 1 vertices. And most especially for this talk, Cry is an example of a flow polytope coming from the complete graph. So this is where we start. Okay, so I'm going to tell you what a flow polytope is. But first, let me tell you what a polytope is. I think a lot of people in the audience, I know from conversing with many of you that you already know what a polytope is, but for anyone who doesn't, here's a quick overview. So a convex polytope is a generalization of a polygon. I'll also be leaving off the word convex. Polytope will just mean convex polytope. And there are two main definitions of this, which should turn out to be equivalent. So the first one is that a subset of Rn is a polytope if it can be written as the convex hull of finitely many points. So what is convex hull? Imagine I have these points in the plane here. Convex hull is just imagine putting a rubber band around like the points in the largest possible way, and the space that the rubber band encloses is your convex hull. This can be formalized, of course, with equations, but this is the intuition. And the other equivalent definition is that a polytope is the intersection of finitely many half spaces if your intersection is a bounded compact set. So for example, here's my coordinate axes, take a hyperplane, take another hyperplane and intersect them, another one and intersect them, and then the intersection of these half spaces, is bounded in Rn, so this is a polytope. And then in the title, I say I'm going to compute something about f vectors. So the f vector, another disclaimer, I'm going to go back and forth without thinking about it between saying f polynomial and f vector. These are the same thing. You can just write, if you write it as a vector, you call it a vector, but otherwise you just put the entries of the vector as a polynomial, and then the f polynomial. This basically just keeps track of the I-dimensional faces of your polytope. So notice the weird notation. This is actually not very standard, but some people use it, and I'm using it because we need it for the talk. Your first dimension starts at -1. This is the empty face is always dimension -1. So for example, for our polytope here, there's the empty face, which is always corresponds to this 1/x. Then you have 3 vertices. These are 0-dimensional polytopes, so that's a coefficient of 3. 3 edges, so that those are 3 1-dimensional faces, so 3x to 1, and then 1 2-dimensional face, the whole polytope, so the coefficient of x squared is 1. Yeah. So any questions about polytopes or f vectors?
So is it that the exponent is the dimension and the number of faces is actually the coefficient?
Yes, you're absolutely right. I added this slide last night, realizing I didn't have any. Yeah, you're absolutely right.
Okay,
So
cool.
was pointed out by Blake. This is x to the number. This is x to the dimension. Yeah, the exponent is keeping track of the dimension, and the coefficient is the number of faces of that dimension. Thank you. But hopefully the example makes it clear. Are there any? Yeah, thank you for pointing that out.
Yeah, is this bijective?
Good. So bijective.
Like given an f vector, can I construct the polytope or no?
Great question. So this is a famous problem, actually. The answer is it's not bijective. Yeah, it's not bijective. You can have multiple polytopes with the same f vector. This was actually open for a long time. And now the new open problem is I think this is the open problem, the state of the art, which vectors can appear as the f vector of some polytope. Yeah, I think, but there's a whole bunch of stuff about this. Yeah, good questions. Other questions? All right, so I really need to tell you what is a flow polytope. So that's what this talk is about. A flow polytope is a special kind of polytope we get from 2 pieces of input data. We need a directed acyclic graph on vertices 1 through n+1, and we need a vector of integer numbers. So we'll call this the net flow vector. It has n degrees of freedom, a1 through an, and the last entry of the vector is going to be negative the sum of the ai's. So we only have n choices here. Okay, so a flow polytope determined by G and A is the set of all flows, namely functions, from the edge set to the non-negative real numbers, where the net flow at vertex I is AI. So, for example, so imagine we have this graph at left with net flow 1, 0, -1. Then let's think about some possible flows. So a function from edges to positive real numbers, that's just like kind of like a labeling of the edges with real numbers. And for example, this I claim is a valid flow. Why? Because at this first vertex, we have the edges coming out. We have 1/3 plus 2/3, that equals 1. At the second vertex, we have 1/3 plus 2/3 minus 1/2 equals 0. And this last vertex, we have -1/2 equals -1. That's an example of a flow. But then there are others. So here's another example of a flow, and you can see that this is also a flow for the same reasons. It satisfies these equations. And I claim more generally, if there's X amount of flow on this first edge, this bottom edge has to have flow 1 minus X for the first equation to be true. And then if there's Y units of flow on this next edge, then on this bottom edge, there has to be 1 minus Y units of flow for the same reason. And so in particular, this is a technique we often use in flow polytopes. We find how many degrees of freedom we have. So for example, here we only have 2 degrees of freedom, X and Y. And so this polytope is living in 4-dimensional space because there's 4 edges. But in reality, we say integrally equivalent. We can project down to 2 dimensions. It's integrally equivalent to this unit square. So integral equivalence is just there's some affine transformation that preserves the number of, it preserves the integer points. Okay, so any questions about, so this is the definition of a flow polytope. Any questions before we move on?
Sorry, what do the integer vertices on the square represent? Like the 0, 1, the 1, 1?
Oh, so those are just representing the coordinates in R2. Yeah, did I answer your question? Sorry, I'm not sure. I might have misunderstood.
I meant, how do they correspond to the original directed graph?
So yeah, they correspond to the parameters X and Y. So yeah, we can basically take, so this I'm not sure if people can see my cursor. Are you able to see my cursor?
Yes.
Oh, awesome. So yeah, so we take the flow polytope determined by this situation has 4 dimensions, like given by each of the edges. But we can see that this dimension and this dimension are kind of redundant because they involve X. They're predetermined by X and predetermined by Y. So basically, we take the flow polytope and project down to just the dimensions having X and Y, forgetting about these coordinates. And that gives us an XY in R2. And the points we can get by doing that projection are the unit square.
Oh, okay, I understand. Thank you.
Yeah, great question. Other question?
I think I'm a little confused. Okay, there's a question from Alex in the chat, but also maybe while you're answering that, I'll try to check my understanding.
Okay, yeah, let's see. Vertices of flow polytope. Fantastic question. I will answer it in a few slides, but basically, yes. Well, not always spanning trees, but I'll show you in just a second. Yeah, so the question was, are the vertices of the flow polytope always the spanning trees of the original polytope? Yeah, you shall see. Yeah, and actually, yeah, your question.
So here, could we just do a calculation of A1 just to make sure the flow, like if A was A1 here, it would be the flows out of the first vertex, right?
Yeah.
So
So
that
if
would
A was A1,
Mm-hmm.
so you're saying in the tuple A1, yeah. Mhm.
Yeah. So if we're checking it for A1, that would be the flow from out of this leftmost point out. So that would be -2. Is that, or no, it would be X and 1 minus X.
Yes. Yep.
Okay.
Yeah, exactly. You take the sum, edges going in one direction, you sum, edges coming out, you sum, edges coming in, you subtract, or you can take the opposite convention, it'll be equivalent. So you take X and add it to 1 plus X, and whatever that is has to be equal to the net flow plus the vertices coming in. So for example, at the second vertex, we have X plus 1 plus X has to be equal to 0 plus 1, Y plus 1 minus Y.
Yeah. Okay. Awesome. Thank you so much.
Yeah, I love the questions. Thank you.
I also have one question since
Yeah.
we're
Yeah.
on understanding things. How does A influence the polytope that we have at the end? Does it really make sense what we choose for A, or if we had 2, 1, -3, I suppose, would we have the same result, the square again?
I just have to say I'm loving these questions. These are all fantastic questions, and I wasn't expecting to get usually when I give a talk, I don't get questions. So this is amazing. Yeah, so the answer is it does it will influence the structure of your polytope. So the disclaimer disclaimer is in this talk we'll only be dealing with non-negative entries except for the last one. But in general, negative and positive will make a big difference. But if you're working in this non-negative place, then the structure of the polytope is actually completely determined by which entries are non-zero. So like you said, if I change the net flow to 2, 1, would that change things? It would, because now we have, this is still positive, but now this is positive, and that's going to change the structure of the polytope. And in general, so I'm talking about the face structure in this talk. In general, net flow, any change to the net flow vector will change for example, the volume of the polytope. Because you can like, for example, if you have, imagine you have this and then you multiply everything by some letter t or number t, then that's the same as dilating your polytope by t. And yeah, so there's all sorts of things you can do with the net flow vector. But yeah, did I answer your question?
Yeah, of course. Thank you.
Awesome.
Yeah, there's one more clarification question in the chat.
Yes.
So for your example, is the net flow vector 1, 0, -1?
That is correct. Yes, that is enough. Yep.
Also
Great.
a question for me. So does the flow of polytope, is it like, a phase-based thing where each point will tell you a possible flow?
Yes, absolutely. Yep, that's a great way to think about it. Every point in the polytope is some flow along the graph. Yeah.
Okay.
All right. Great. So yeah, so one of the ways that we tend to study flow polytopes is we study whole families of flow polytopes at once based on families of known graphs. So for example, what are some graphs we know? Well, one of the first graphs we might think of is the complete graph. And that's what this talk is going to be about. So in the literature, the family of flow polytopes coming from the complete graph, this is denoted by flow NA. And you'll notice I skipped over these words transitively directed. What I mean by this is just there's many different ways to direct the complete graph, but you'll oftentimes get cycles. We need our graph to be acyclic because we want a polytope. So we direct them all from just like put them in the plane, direct all the edges from left to right. So for example, here's an example of flow 3, A1, A2, A3. So it's the complete graph on 4 vertices, and you get hyperplanes. There are hyperplane descriptions as follows. So for example, at this first vertex, we have x12 plus x13 plus x14 equals A1. And we get our second hyperplane, x23 plus x24 minus x12 equals A2, and so on. And in particular, when you have n vertices of your graph, you'll have n minus 1 hyperplanes because the last hyperplane is kind of redundant. This is just a thing. Okay, so what has been studied for this family of flow NA before? So the first thing is our motivating example, the Chan-Robbins-Yuen polytope. This is an instance of flow NA, and you can get that by setting A equals 1, 0, 0, 0. Oh, and by the way, from here on, I should have said I'm also leaving off the last entry because, again, it's completely determined by the previous entries. So you'll only see non-negative things, but the last entry is just the negative sum of the AIs. Okay, the other thing that's known is Mazaros, Morales, and Rhodes in 2015 showed that in the case that all AIs are strictly positive, this is combinatorially equivalent to a product of simplices, delta n times delta n minus 1 down to delta 1. However, the F vector for other cases is harder to compute. And there's many explanations for this. One possible way is to explain that the flow n where all the AIs are strictly positive, this is a simple polytope, whereas general instances of flow NA are not. Okay, so the main goal of this project was to compute the F vector of flow NA for arbitrary non-negative A. And the punchline is we were actually able to do it. But first, some motivating data. So, because you might be thinking like, of course, the first thing to do is to plug it into OEIS, right? So you can see some of the patterns we saw before. It has 2 to the n vertices, 1, 2, 4, 8, 16. The codimensional faces are also something in OAS, just some, I actually forget what they are, but they're also not hard. But then you might be looking row by row, which is what we want to do. And you see, okay, this is nice. We have some binomial coefficients, more binomial coefficient looking things. And then you get to 5 and you see, oh, wait, now the symmetry is lost. And it only gets worse from there. Like once you get up to 7, 8, 9, it's, numbers aren't in OAS and they're not very tractable. But I can tell you how we can get them.
Can I ask about the data?
Yes.
So yeah, this look really nice. What happens if you do the H transformation?
Yes, to get the H vector instead of
Yes, do you
so
have an
this is a great
understanding?
question. So my disclaimer is I have limited understanding of the H vector, except I know how to do it in the case of what do I mean? Simple polytopes or simplicial polytopes? Which do I mean?
Yeah. I'm not
Yes.
sure how it's defined either. That's why I asked about the transformation.
Ah,
But the thing
yeah,
is,
it's a good question.
I studied some similar vectors like F-star vectors, and they're almost never symmetric. So I'm surprised to see you having symmetric examples. And I'm wondering, what are the H-star numbers that generate them?
Yeah, this is a good question. And I guess a professor, so I gave the talk, and a professor here at UMass told me that I guess, so I don't think I can do the H vector just in general, but there is this what's it called? There's a variant of that. Maybe this is what you're referring to actually, that you can do for any polytope. And so I meant to look into this, but just haven't had time because I wanted to put this out.
I was curious, thanks.
Yeah, thanks for asking. Yeah. Any questions before we move on to faces? All right, so faces of flow polytopes. So, I see there's some chats. Hopefully yes, exactly. Toric H vector. This is the word I was forgetting. Thank you for adding that. Yeah, so one of maybe the biggest thing I want to convey to you in this talk is, of course, maybe the definition of flow polytopes, but also this following powerful theorem. So the idea is if you can show that your polytope is a flow polytope, you have a very powerful technology for understanding its faces. So this is a theorem due to Hille in 2003. It was known before, in the case of vertices at least, to Gallo and Sodini in 1978 in the context of optimization. Let me read what it says, and then I'll explain some more. So it says that the d-dimensional faces of our flow polytope correspond to subgraphs of G that have first Betti number equal to D, and which are the support of an A-valid flow. Okay, so the two things here that I need to kind of explain. First Betti number, this is just the number of edges minus the number of vertices plus connected components. Or if you're topologically inclined, it's the dimension of the cycle space. This is actually very helpful when the graph is planar. You can just literally count the cycles you have on your graph. And the support of an A-valid flow. So it sounds bad, right? But I'll give an example in a few minutes, and you'll see actually this is not only not a flaw, it's actually a feature. It means that, sometimes finding all subgraphs of a graph is very, very hard, but this condition being the support of an A-valid flow, it limits the number of subgraphs we have to look at, and actually oftentimes makes the problem tractable. But what it means, and in words, I'll give an example again, but it means in words that your graph can be found as the non-zero entries of a flow, of some flow. There exists some flow for which your graph is the non-zero entries. Okay, but let's see an example of this theorem. And this gets back to Alex's question. So in the case that you have the net flow 1, 0, 0, -1, your vertices, so okay, let's just jump into this example. Your vertices of the flow polytope in the case of 1, 0, 0, -1 will be exactly spanning trees such that your spanning tree starts at the first vertex and ends in the last vertex. Like you won't have leaves. Okay, actually, let me generalize that statement. For any net flow vector, your leaves have to occur. So your vertices will be trees where the leaves have to occur at sources and sinks. So it won't necessarily be spanning depending on how big your graph is, but it'll be related to trees. So for example, here I have a subgraph. It's a 0-dimensional graph. Sorry, it has a Betty number 0. So it should correspond to a 0-dimensional face. And this is exactly what we see here. You can realize this as coming from some flow by setting x equals to 1 and y equals to 0. And that gives us the vertex 1, 0. Okay, similarly, I can take a different graph, say this one in red, and now I can realize, so it's all, again, has Betty number 0, there's no cycles, corresponds to the 0-dimensional face, and I can, again, realize it by setting x equals to 0 and y equals to 1. Here's the correspondence completely. So, for example, the vertices have no cycles, the edges each have 1 cycle, and the whole polytope is 2-dimensional, so it has 2 cycles. And you can see it's even nicer than that. The statement extends even to like face lattices. So for example, what if I want to talk about, you know, the edge containing this vertex and this vertex? Well, I just take the edge union of these two graphs, and then I get this one, and that's this graph, which is the union of those two, is the edge connecting those two vertices. Yeah. Any questions? So this is maybe one of the biggest takeaways of this talk. If you have a polytope, if you're doing polytope research and you can show your polytope is a flow polytope, you have a lot of power to understand the faces. Okay, so here's an example of something that's not A valid. Now here A is again 1, 0, -1. This isn't valid because there's no way of taking this graph and making it the support of a valid flow. Because, for example, I have to have a 1 here, this first vertex, but this last vertex has to have -1, but there's no way to get flow over to that vertex. So oftentimes this valid condition, really what it does is give you something about the connected components or something like this. So it's, again, it's actually a very nice, like you can see, for example, all these graphs are connected, whereas this is not. It usually just limits the number of subgraphs you have to look at. Okay, so we have everything we need to understand the main results. Yeah. So you might think, okay, we're back in the Chan-Robbins-Yuen polytope case. Imagine that we apply this previous theorem of Hille and Gallo-Sedini to the faces. Like, what are the subgraphs of the complete graph that correspond to faces of the Chan-Robbins-Yuen polytope? And the answer is this. So these are subgraphs of the complete graph where every vertex lies along a direct path from the first vertex to the last vertex. But turns out we weren't the first people to get here. So it turns out this exact set has been studied before in a completely different context. So this is a paper by Andresen-Kjeldsen in 1974. And they studied exactly the set. In fact, I used omega because this is their notation. They studied the set and they enumerated it and did many different things, computing generating functions and recurrences, etc. with the set. But they weren't working on polytopes. They were working in automata theory. And in particular, you might ask me, what were they doing with automata theory in this context? I actually can't answer you because they cite a paper. They say, based on our work in automata theory, and they cite, but I can't, the paper is non-existent, or maybe I just can't find it. Maybe it's behind a paywall or something. But yeah, I don't know. I've never been able to find that paper. I've looked a lot. So, but anyways, this paper is very nice. It's very self-contained. But I don't know why they were looking at it, but it's very nice. Anyway, so they were able to enumerate omega n, but they did so by taking an intermediate step. So they first enumerate a different set of graphs, which they call primitive subgraphs. So primitive subgraphs, these are graphs which are in omega n, but they also have all vertices contained in a single connected component. I will often refer to this as using all the vertices. So on the left, we have a primitive graph. It's going to correspond to some face of the polytope, but in particular, all the vertices are in one single connected component. Whereas on the right, they're not. There's multiple connected components. So I'll say the graph at the left uses all the vertices, the one at the right does not use all the vertices because we're kind of skipping these two. Questions about what it means to be primitive? Okay, so the main thing to say here is that they were essentially, now that we've kind of upgraded our language to flow polytopes, they were working essentially in the case that A is 1, 0, 0, -1, but the same definition works for any A. This definition is not dependent on A. So we'll refer to primitive graphs in the case of any A. Okay, so let's bring this back to flow polytopes. This is maybe the second biggest thing I would like to convey in this talk. It's still kind of a background, but very nice. So from Hille's theorem, what is the F polynomial? Well, this whole talk hinges on this fact. The F polynomial of a flow polytope is a generating function over the set of A-valid subgraphs where we're keeping track of the first Betti number. And why is this important? So we can take this the definition of primitive that they have, Andresen-Kjeldsen, and upgrade it to a new definition of F vector. So now we're going to define the primitive F vector for a flow polytope. We'll denote it as Fna if it's a vector. More often I'll be doing Fnax, or actually I really mean F polynomial. This will be a generating function over the set of A-valid subgraphs that are primitive and keep track of the first Betti number. So it's like kind of like a subset of the F vector. I mean, of course, the F vector is not a set, so you can't do that. But so here's some more motivating data. Once again, the number starts. So these are the primitive F vectors for in the case of this cry, and they start off by looking nice, but then again they get not so nice. But maybe the punchline is they're still nicer than the F vector. So we're actually going to be able to solve the problem using these. Okay, and then my favorite slide of the whole talk. So this kind of summarizes everything we've learned so far before we kind of get into results. So here are all of the A-valid subgraphs. In the case that A is 1, 0, 0, -1. So I'm using all my examples for cry. Again, we have this for general A, but and let's see how we can read off the F vector from this data. So this 1 corresponds to the empty face, which corresponds to the empty graph. So I'm leaving it off this table. This 4, this should correspond to the 4 subgraphs having Betti number 0. And that's exactly what we have here. 6, there's 6 subgraphs having Betti number 1, 4 having Betti number 2, and 1 having Betti number 3. The primitive F vector is this basically the same data, but now we only look at the ones that use all the vertices. So the empty graph doesn't use any vertices. So we just, have it as 0. In these first 4, there's 1 that uses all the vertices, namely this one. There's 4, 1, 2, 3, 4 that use all the vertices here. We have to exclude these 2 because they don't. And then 4, 1. So we have in this picture, Hille's theorem giving us the F vector for cry and also the primitive F vector. Any questions about this? Okay. Yeah, so then we're able to state our first result. You might be thinking, okay, you promised me F vectors. Why are we talking about primitive F vectors? Well, the answer is because we can completely reconstruct the F vector from this new definition of primitive F vectors, and we do so like so. So the statement looks technical, but it's actually very nice. So we're interested in this F, well, say F polynomial. We sum over netflow vectors that are less than A, where B is basically obtained from A by deleting some subset of the zeros in A. And then we look at basically the primitive F polynomial of that B. And then KAB is just the number of ways of deleting those zeros. So it's a very combinatorial problem. So for example, I want to compute the f polynomial of 1, 0, 0, 1, 1, 0. Well, I take 1 over x, and then I add this vector. So now these are on the right hand side, these are all primitive f polynomials. This one I've deleted no zeros. This one I can delete this 0 or this 0. So that I can get basically this net flow vector in 2 possible ways by deleting this 0 or this 0, which is why there's a 2. I could delete this 0, that happens in 1 possible way, so I get this one. I can delete both of these zeros, it happens in 1 possible way, so I get this one. I can delete this one in 1 of these and get it with multiplicity 2, and then I can delete all 3 zeros and get it and get this one. Okay, so basically, the moral here is we can completely get the f polynomial as a sum over primitive f polynomials. And then the proof, I'm going to omit it, but it's kind of illustration of the proof is like, so you basically take a graph corresponding to some face that you're interested in, and you just push it down to a primitive graph where you're no longer skipping vertices. That's kind of the idea. So like, yeah, I won't say more than that unless people want to hear more later, but that's the idea. Okay, so this is where things start to get a little bit technical, so I apologize, but basically we need 2 definitions in order to state our main results. And yeah, they're a little bit hard to state, but at the same time, they also may look familiar if, yeah, they may look familiar. So the first is this definition of a reverse composition. So we'll, given some net flow vector A, we'll define a reverse composition, rev comp A, as follows. So we're going to read the entries of A from right to left. We're going to inductively create a block whenever a new non-zero entry is encountered. And then we're going to return the tuple sizes coming from this list. Okay, so here's, oh, and I should say this might look familiar. Why does this look familiar? If you're familiar with the bijection between compositions and binary vectors, this is basically exactly that. It just kind of doing it in reverse. That's why we call it reverse comp instead of maybe comp. And this was necessary for technical reasons, which I won't get into. But here's an example. So we have the net flow vector A. We read it from right to left. So we have 0, 1. We stop because we hit a non-zero entry. So that's our first block. And then we keep reading 0, 1. We get another block. 0, 0, 1. We get another block. And then finally 1. So these are our blocks. And now rev comp A is just return the sizes of those blocks. 2, 2, 3, and 1. And so that's our composition. Any questions about this? Okay, so the second definition we need is this notion of a special polynomial. So this is a polynomial depending on some composition alpha. And this again may look kind of familiar. So we're summing, so given alpha, we're summing compositions beta greater than alpha, where the order that we're using is reverse refinements. I'll give an example of this in a second. But we're taking reverse refinement on compositions, -1 to some power, and then a product of monomials, sorry, a product of variables determined by beta. So just xi to the beta I for your composition beta. So I'll say what reverse refinement is in a second, but why does this look familiar? If it does, it's because there's a very similar formula, or this looks very similar to this change of basis formula for writing monomial quasi-symmetric functions in terms of Gessel's quasi-symmetric functions. It's also reverse refinement. It's also -1 to this power. And the reason for this, I mean, there's, I guess it's still work in progress to see the full reason for this. But one side of me kind of believes these days that actually maybe this is just kind of coincidence. This change of basis formula is kind of just inclusion exclusion. So in some sense, this this formula is, you could think of it as, oh, it's basically just inclusion exclusion. At the same time, I think there's something to be said because we have the same partial order with the compositions and I think, yeah, maybe saying that there's a connection to quasi-symmetric functions isn't fully right, but this is basically a quasi-symmetric polynomial, but it's missing a few terms. That's maybe the best way to say it. I'll go back to that later. Reverse refinement is this order. So basically you take compositions and you can go up if you can take a composition and write it, one of your parts of the composition, and write it as a composition. So for example, 2, 2, we can take this 2 and break it into 1, 1, or we can take the first 2 and break it into 1, 1, like so. And you just go up that way. In general, these should be, I think, just Boolean lattices. Okay, and so our first result is that the primitive f polynomial. So first we take our vector A and we write it in terms of as a composition using this revcomp function. Then our primitive f polynomial is just an evaluation of this special polynomial. And the evaluation is also not too bad. It's just you take x plus 1 squared minus 1, and then in general x plus 1 to the I minus 1. And that's all it is. Yeah, and so this this lemma is kind of the key thing that we need to solve everything else. So I apologize. This is where it gets technical. So I will maybe try to go through this rather quickly. Also, as we're getting to the end, I think I'd like to give time for questions. But if you have questions, definitely don't hesitate to ask. Because I think if you want to, to expand upon any of these results in any way, this is kind of the lemma that maybe would need to be changed in some way. Anyway, so I'll include the details, but I apologize if it's a little technical. Yeah, so the way we prove this is you start by basically converting some subset of your vertices to just sets. So the idea is the first vertex and the last vertex don't really play don't really influence the combinatorics in many ways. So we just look at the subsets of V2 through Vn. Remember our polytope, our graphs go to Vn plus 1. This is why, so we're looking at just V2 through Vn. And we're going to associate to some subset of these vertices an indicator set in the usual way, but we're just shifting things by 1 so that our set ST is going to be, a subset of 1 through n minus 1. All right, and then for every such set, like this should really be like S sub t, we're defining Rs to be primitive graphs of the complete graph that satisfy 2 conditions. These conditions seem weird at first, but then you'll see why we're doing them in a second. So the first condition is that the out degree of every vertex has to be positive. That's not too bad. The second one's a little weird. We're saying that for any index that's not in your set, this implies that the in degree is 0. So the in degree of Vi minus 1 is 0 because everything's shifted by 1. So saying it a different way, Rs is the set of primitive subgraphs of our complete graph for which all vertices have non-zero out degree, and where S is keeping track of vertices, again, shifted by 1, which are allowed to have non-zero in degree. They don't have to have non-zero in degree, but they can have non-zero in degree. Okay, so this is where an example is really helpful. So imagine we have n equals 3 and s equals 1. So n equals 3 means we're working on the complete graph with 4 vertices. Or we're dealing with primitive subgraphs, so we're using all the vertices. And s equals 1. So now that means that the second vertex, because I shift by 1, the second vertex is allowed to have non-zero in degree. So all the vertices have non-zero out degree, but the second vertex is allowed to have non-zero in degree. Am I saying this right? Yes. So you can see here it has 0 in degree, but it's allowed in these 2 vertices to have non-zero in degree. Yeah. And any questions about that? I realize it's, again, rather technical. All right, so the reason that we're doing this is that this way, if S is a subset of T, then Rs will be a subset of RT. This is why we're doing this. And we want our sets nest in this way because then we can do inclusion exclusion. So the idea is that our set of where we're trying to find the set of all primitive cardinality of all primitive subgraphs, we can just take inclusion exclusion over intervals of the Boolean lattice, and we're taking the cardinality of these sets. Excuse me. But now the idea is we want to keep track of the first Betti number in order to get the primitive f vector. So the way we're going to do this is we're going to upgrade to generating functions, but first we need to say why primitive subgraphs are so important this whole time. So the idea is if your graph is a primitive graph, then you can compute its first Betti number immediately. Its first Betti number is completely determined by the out degrees of its vertices. The sum of the out degrees of its vertices. So h is primitive means that the first Betti number is negative n plus the sum of all the vertices, the out degree of all the vertices. And this is basically just a modification of like the handshake lemma and the definition of first Betti number. All right, so we're going to now enumerate for each s the number of graphs and keep as a generating function basically these Betti numbers. Okay, so let's see an example of RSX for the set s equals 2 and n equals 3. So this is now the set R sub 2 when n equals 3. And I've ordered them by row according to their Betti number. So the ones in blue have first Betti number 0. The ones in orange have first Betti number 1, and the ones that are green have first Betti number 2. And you can see that they also have consistent out degrees. So the sum of all the out degrees of blue is 3. Sum of all the out degrees in orange is 4. And sum of all the out degrees in green is 5. And that's, so our generating function over the set is x to the 5 plus 4x to the 4. This is the typo, it should be 4x to the 3 because the sum of the out degrees is 3. So this is exactly how we get our generating function. But the crazy thing is that it factors. And in general, it'll always factor in this way. So why does it factor in this way? And I think I want to wrap this up soon so I can get questions. But the idea is you basically read the graph from right to left. Actually, maybe I won't give this explanation, but if people want to see basically why this factors in this way, I can give an explanation. It's recursive and involving generating functions and quite nice. Actually, maybe I'll just say it very briefly. It's like x plus 1 squared means either take the vertex or don't. And you have two choices of doing that. And the minus 1 is basically saying we have this condition that all the vertices have positive out degree. Well, this is basically subtracting 1 because we need, if you don't choose anything here, then you're basically, you're taking the empty graph. So you're violating that condition. So you have to subtract 1. Anyways, that's probably too fast. I can come back and explain more if people want to hear more details. But needless to say, these always factor. And that's exactly how we're getting this evaluation of this polynomial. Like x plus 1 to the I minus 1. All right, and then finally, as I mentioned, the sets nest in this way. So this is just a visual example of how they do that. So we want the graphs that are just at top in black, but we take R12 and then we get the ones in green and red that we have to subtract off. We doubly subtracted off the blue, so we add it back in. So basically, this is just saying that inclusion exclusion really does work because these graphs, these sets of graphs are nested. Okay, so we made it through the most technical part. I'm just going to kind of flash some results now and to show you how they specialize in various cases. So we found the primitive. So far, we've found the primitive f vector for any flow polytope over the complete graph. This specializes to the cryopolytope as follows. Again, it looks very technical, but it's actually not. I can break it down. So it's a sum, and we have two main pieces of the sum. This pi, this is just I'm calling it pi because it specializes, or sorry, it specializes to a result of Andresen-Kjeldsen. They use this notation pi, but this pi is just an evaluation of a Q factorial, and it's basically, you can think of it as just a product of these special factors x plus 1 to the I minus 1. And then for each term, I said that there was this connection to quasi-symmetric functions. The reason I was phrasing it that way, instead of just saying, oh, it's inclusion, exclusion, is because in this special case, we get legit symmetric polynomials, namely complete homogeneous symmetric polynomials, basically whose degree changes based on which term you're in. So basically, this is all to say that the primitive f polynomial for Cry is quite nice. Involves some interesting objects like symmetric polynomials and Q factorials. And then basically going a step further, combining our relationship between the primitive, so like now we have the primitive f polynomials, we have a relationship between f polynomials and primitive. So we combine those, do a lot of work, spend many months, and find this formula for the f polynomial. So this is for any flow polytope over the complete graph. It's again just a sum over the same relation, this reverse refinement. Have this product, have this evaluation. I think in the archive paper I put out, I found a slightly nicer way to write this. So take a look at that if this looks a little bit too messy. But then maybe the thing to say is that it looks a little bit messy. It's actually extremely computationally efficient. So I think it's kind of cool that we finally have something like this. And maybe the main feature of the show, so specializing to the case of 1, 0, 0, we get the first known formula for the f polynomial of Cry. And it again, because of this 1, 0, 0 thing, we again get homogeneous symmetric functions. And again, in fact, you might think, is that even a different formula? But there's just a few minor differences between this one and the primitive one. It should be one of those games where you have like the two images next to each other and you have to find the difference. Like what's different between this one and the next one? Yeah, but so how do we recover other people's results? So, I had told you Andresen-Kjeldsen had a formula for the whole set, and indeed, so this should be true, that if you evaluate x equals to 1, we get the result, and you do. This is what the result looked like. And again, now you can see more clearly why I'm using this notation pi x. They just have a pi because their pi is just a product of powers of 2. And the other end of the extreme, so that's if we set x equals 1. And then if we take the previous formula for all of these, for any flow polytope over the complete graph, and set a equals 1, 1, 1, 1, 1 instead of 1, 0, 0, we get the other extreme, which is the result of Mazaros, Morales, and Rhodes on tensor polytopes. And that's just an evaluation of a Q factorial, which is the f polynomial of a product of simplices. Okay, so that's my talk. I have one more quick thing to say, because I think it's interesting, and I wanted to give you a flavor for if anyone's interested in doing further work on this. This topic is somehow related to many, many different combinatorial objects. It's quite exciting. I've only been able to give a small taste, but I want to give one more taste. And that is a connection to primitive Fishburne matrices, which are also, as a side note, connected to these unit interval orders that appear in like Stanley-Stembridge conjecture type thing. So like, yeah, I don't even fully know the full connections, but so a Fishburne matrix is an upper triangular matrix with natural number entries such that no column nor row is a zero vector, and it's primitive if it only uses entries in 0, 1. So it turns out there's a very simple bijection between primitive faces of Cry and primitive Fishburne matrices, and this is why we're redundantly using the word primitive. So if you take your Fishburne matrix and you turn it 45 degrees, you have ones. You place a edge for every 1 and a non-edge for every 0, and then you have your primitive face of Cry. So there's just this very quick correspondence to go between them. And why am I mentioning this? Well, because then I can state one more result. So it turns out that we were able to find a generating function like so. So if fdn is the number of d-dimensional faces of Cry, then that's equal. We were able to show that these numbers are equal to the coefficient of abstraction t to the n x to d of this generating function. So I thought it was a kind of cool result. It's actually not such a big deal insofar as it's very quickly obtained by this connection to Fishburne matrices. So actually you can prove it also. We first proved it with the other results we had. But then there's this connection. So Jelinek in 2011 had a multivariate generating function formula for these primitive Fishburne matrices. And by using this connection, this bijection between the two, you can basically just evaluate Jelinek's generating function and get this immediately. But anyways, this is more to illustrate that there's connections between these faces and various other combinatorial objects. Final remarks. This is perhaps one of the most mysterious results. There's this cool different relationship between the F polynomials and primitive F polynomials, which we're able to prove algebraically, but we highly believe suggest some kind of geometric meaning. And so that remains open. And of course, we're also looking to extend the results to various families of subgraphs and to also allow for negative entries in our netflow vector. So open problems. So there's analogous statements to this in Andresen-Kjeldsen's paper without the X. And basically, they ask for a combinatorial proof. So they also only have an algebraic proof. They ask for a combinatorial proof. And that remains open to this day. So actually solving this, proving this one combinatorially would be better because it gives you more restrictions. It gives you essentially more information about how the bijection should work. And if you did that, you would also solve their open problem as well. So just an advertisement for that. It's something I'm thinking a little bit about. So if you want to work on it, maybe just let me know so I know, what the state of the art is. So the first open problem would be to find a combinatorial proof of that. The second would be this strange polynomial p, and also the sum over homogeneous symmetric functions. Someone asked me when I explained this in a talk, like, what if you don't evaluate? Does that correspond to some other combinatorial object? Also, what happens if you evaluate it in other ways? And these are open questions. And finally, I think the big next direction is to show or to use these same notions, these new notions of primitive F vectors, to try to compute F vectors of other flow polytopes. I think that it's not clear how far this technique can go, but I think it can definitely keep going. Maybe it can go very far. Yeah, so some references, my new paper on the archive, feel free to check it out and send me comments and feedback. Thank you so much for listening and also for the invitation to talk. Oh, I think Anastasia is saying.
Yeah, I'm totally muted. Yeah, thanks so much. Sorry. Yeah, thanks for a great talk. And I'm so glad you had so many examples. That is so helpful to me, at least.
Oh, so good. Yeah, thank you.
Yeah. Anyone have questions that want to start us off with?
Sorry if I missed it. My laptop kind of died for a while. Did you ever bring it back to what you were saying at the beginning?
Sorry, did I ever?
You said at the beginning that it related to the other talk from I think last
yes.
week. Or, yeah.
Thank you. See, I did forget. Just like yeah. So the thing is that yeah, thank you so much for reminding me. The idea is that one of the things for polytopes in general is like one studies their faces and F vectors and face lattice. Then one studies their volume and Ehrhart polynomials. and one studies are integer points. And somehow like whenever I'm talking about faces, I forget to mention the others. Yeah, so the connection to the previous talk, so these costant partition functions, it turns out that the integer points of a flow polytope are exactly constant partition functions. So the number of integer points is exactly an evaluation of a constant partition function. So something I wanted to bring up was, yeah, in the talk last week, we saw that there's these, generalizations to Q. And as far as I know, I don't think that's been, I could be wrong. So, but I think it would be, I don't know if anyone has sought that generalization in the flow polytope framework. So I think that would be a really interesting thing to pursue. Yeah, so it's not a, yeah. Yeah, thanks for reminding me.
Yeah, thank you.
Another thing you mentioned at the beginning was something about Catalan numbers.
Yes.
What's that about? I forgot what you said in the beginning, and
yes,
now
absolutely.
that we know the definitions.
Yeah, and sorry, I should have also made it clear there. Thank you for asking. So this concept of like, one studies these different parts of the polytope in terms of like, you do their faces, you do their integer points, you do their volumes and Ehrhart polynomials. So I should have mentioned, this is one of the reasons that Cry is so famous. So its volume is equal to the product of n-2 Catalan numbers. So that is something I do think about from time to time, like trying to prove this combinatorially. But yeah, the reason I should have said this earlier, it wouldn't come up in this talk just because for this talk I was just doing like the faces, and so I forgot to mention this. This was more motivating, like why this polytope is famous. But yeah, the volume and like so far this, like I wasn't able to make any progress on its volume besides what's already known.
Okay, thank you.
Yeah. But this is an interesting problem to try if anyone wants to try it. It's like, because you think it sounds very we all love Catalan numbers, right? So it's an interesting thing. So there's, again, there's proofs that are algebraic, but there's no bijective or combinatorial proof to something like dict paths or anything like that.
Do you know what's the last entry of the F vectors compared to this number? Could it,
Wait, say it.
is it larger or, so your last entry of the F vector, would it be, do you know if it's always smaller or larger than this number? Than the Catalan numbers? Because in the Ehrhart setting, that would be in the F star setting, that would be exactly, it's the product of the n-2 Catalan numbers.
Oh, because you're saying in the Ehrhart saying the first coefficient is, the leading term is the volume. Is that what you're?
I'm saying the F star, the last term is the volume, because it counts the number of triangles, basically.
Yeah, that's fascinating. So I can say in this data, so yeah, I guess we'd have to do that transformation. So let me think. Yeah, because the last, so these
what
are,
is 4, 8 compared to the?
Yeah, so these are smaller than the product of Catalans because
yeah, because we would have to think of F vectors of triangulation. Sorry, so they would be a little bit larger.
Yeah, but that would be a really interesting thing to do because we have these now. So yeah, thanks for mentioning that. I'm gonna have to give that some thought. Maybe I'll get in touch if I can figure anything out. Yeah, because whenever there's any new development on this polytope or this family of polytopes, I always go back to that problem and say, oh, do I have new technology to find this bijective proof? Yeah, thanks for asking.
Thanks for the great talk and well explained.
Oh, no, thank you.
So in the definition of cry of n, it's like you're taking like the convex hull of a bunch of permutations that like avoid that like region in the bottom left, right? has there been any studying of like if you take a different region, like a different partition, I guess, down there? I guess this is kind of like Stanley-Stembridge conjecture related. Do you know?
Yeah, great question. Yeah, let me think. I actually don't know. Yeah, I don't know. That's a really good, interesting question. In particular, the first thing I want to say is like, I wonder if there's a connection to other flow polytopes, but yeah, I guess I don't know. Yeah, I'll think about that. If I come up with anything, I'll ask, but yeah, thanks for asking. Yeah. Actually, can I ask why do you say it's so related to Stanley-Stembridge? What can you explain your thinking there?
Yeah, so if you take the set of all those permutations that are like that avoid that region, and then you take like the power sum symmetric function of like with like their cycle types, that's like the, I guess, the dual of the chromatic symmetric function for the thing.
Wow, very
So
cool.
it would be
Very
interesting
cool.
to see if there's a relation there.
Yeah, big time. Thank you so much. I'll look into that.
Okay, with that, let's thank William again and pause the recording.
Okay.